Got to turn my fan back on. I hope it doesn't disrupt anyone. For those in Singapore, I'm sure that you can feel my pain of being a very soft European person in some mild heat. So now we're going to look into functions. Now I can't think of a programming language that doesn't have functions. They call them different things, subroutines, methods, what have you. But a function is essentially the same thing in most languages, in that it's a collection of like code. This can be calls to other functions. It can be math operations, as you see here. It can be printing, input, output, what have you. It can be really anything. But essentially, it's a group of code that's put under, or it's put together inside of a block that is then referenced by some identifier. And for instance, writing C code, as you might have seen in the examples that I'm showing or doing, it's just some human readable name, and usually the name sort of explains what it does a little bit, right? So the example in C of a function that you'll always see is the main function. Now, so the main function itself is a function, but we can't call it. Like, we should never call main from within our program. It should only ever be declared once. And why it's important that we call it main, like lowercase m-a-i-n, is because the operating system actually uses this as the entry point into the program, and the operating system sort of calls this function, and that's how it runs our program, right? And so functions are really important to use, mostly because they provide a few sort of they don't necessarily provide good performance. I mean, they do have an overhead, but there's also language dependent, compiler optimization dependent, and for the large scheme of things, not super important. But for instance, what I tell my students and people that I'm writing code with who are getting started when you're doing a thesis or something, is that you want to try and really make use of functions to create logical separation and reusability of your code. Like, having large 100-line functions is a bad idea, because in that function, it's probably doing lots of things in that 100 lines. So you should separate that up into more functions. You sort of keep going down until a function performs a specific task. And you might think, well, this is kind of stupid, we're going to end up with hundreds of functions, but you should go and read the Linux kernel source. It's a ton of functions, but it's, for the most part, you sort of document your code and you can understand what your code's doing because it's calling these functions with human readable names that make sense, right? So it creates this division, and it's very useful when doing this division is that if the function should perform one specific task, right? I've been using, for instance, printf in my examples, and so there are a lot of functions that are come in like libraries. Like in most programming languages, some libraries offer some sort of functionality. They offer certain data types, methods, objects, what have you. C libraries are pretty much the same. They offer you variables, declarations, definitions, and then functions. And if you include standard io.h, you will get access to printf and all of the print statements, all the output and all the input stuff. And so this is how you get, this is one use of functions, is that you can use functions to export functionality of your program. Or so if you could give someone your program and they could easily use the functions you've written to expand its its feature set, or to implement more advanced features or what have you. So a function has a pretty basic structure. It has parameters and a return function, a return value. So I think I'll quickly jump to the next slide. So this is what a basic function, this is an empty function. As you can see here, it's called foo. So this is the name. Void is the data type of the function. And so what this defines is what value the function returns. And so when a function returns, there's one value, you can return one variable of the type given here to the calling task. And so you'll see sometimes in code, it'll write a equals function call, and there'll be some function call. And because the value that this function call is returning is getting stored into a, right? And so that's why I think on this slide, it can return a value back to the callee when execution is completed, right? And so that's what this is telling us, this void. And if we go down, for instance, here, this function has the type int, and it's returning 1. So it's actually returning the value 1. The functions can have multiple parameters, and this is sort of standard to most programming languages, that if you want to do something to certain data or sort of tell the function which logical function it should actually do or implement or carry out, then you can pass it in a flag or a data structure or whatever it is, so that the function actually can have sort of external input from the rest of the program. And so this function here again is doing, like, it's not taking any parameters because these parameters live inside of these brackets. And so this description here is pretty easy and it's pretty simple. This function foo, minimal, takes no parameters, and so we have void. And if we remember back to talking about data types, a void data type means nothing, like it's meaning no value. And so what it's saying here is that this function takes in no value, it takes in no parameters. It does nothing, and we can see this because it's just empty brackets, and it returns nothing because we've defined the function as a void function, meaning it returns void, so meaning it returns no value. And so the general sort of structure of a function is that we have the return type, the function name, a parameter list, so it can be multiple, it's not just one. You can only return one item. It could be a structure or something more complex data structure with lots of values in it, but you can only return one value. And so this is a parameter list, and then obviously the function code within these squiggly brackets. So the more advanced version is that foo now returns a 1. It returns an integer value, and this function will always return 1, right? Taking it even more advanced, we can say, okay, we're going to pass in a parameter. Here it's called bar of type int. So this is saying we want to give this function, every time this function is called, you have to pass it in an integer value. If you pass in something that's not an integer, it will be typecasted into an integer within this function call, and so you can get weird stuff happening. So it's saying foo returns an int, and it takes in an int as a parameter, and it's no longer returning just 1, it's actually returning this value given into it, that was given to it as a parameter, times 2. So an example, do I have an example of this? I think, wait. No, I don't. But we'll go into the parameters a little more in depth, and then I'll demonstrate this in a minute. So we're talking earlier about memory structure and sort of talking about the stack and scope of functions. And so this is one thing that some students struggle with when they're getting their heads around C, is that these parameters that are passed into the function, they are local, like their scope is inside the function. They exist only on top of, like on the function stack. And as soon as this function returns, it returns the return value, but the stack itself is destroyed. And so if the variable exists in the function and it returns, it no longer exists. And these values are not passed in from outside by, like, I mean, if I was to call this int foo and pass in like a variable called a, it would return to me double a's value, but a's value itself would not change because the parameters here they're a separate copy, if you will, of the parameter on top of the function's stack. So they're temporary and they're only valid for the function's execution. If you want to keep a value of a variable, you have to return it, because that way it's sent back to the other scope of where the function was called from, right? Otherwise they're destroyed. So the only way that we can, so this is what I'm saying here, the only other way that we can sort of modify a value within a function and have it valid when we return is to pass in a pointer. And so we're going to talk more about pointers later on, but a pointer is essentially, you're just passing in a location in memory where a value is stored that's separate to this function call. So inside the function, it's going to go, okay, cool, I'm going to go and modify that memory location. And once it returns, the variable that told you where to look in memory is going to get popped off of the stack and destroyed. But as long as you still know where in memory this was, you can still go to memory and get the value, because that memory and value is not on the stack, it was in the heap and it's still there, right? And so this is why passing pointers in, it solves a lot of problems with a lot of functions, not having to make you create large data structures to return multiple values and what have you, right? So now we'll look at the hello world example now that we've sort of talked about functions, and we can talk about a few things. I sort of mentioned we have this main function, and so this is really just a function like any other function. You can see here empty parameter list, so it takes in no parameters. And it, like as I mentioned, everyone has to have it, it can't be called, and it's the entry point, right? Now the return statement, main it returns either 0 or an error code to the operating system when called. If you don't return something, it will return 0 by default, but generally programs will use a non-zero number to represent some sort of an error code. But returning 0, and just in general, 0 means success, because it's easy. You only have one value of success, but you generally want to differentiate between failure, and therefore you're saying every non-zero value is failure, and you can sort of create error codes that have certain meanings and whatnot, right? So we now have, we know what a function takes in, how we sort of give it its return value data type, and like its parameters and return values and blah, blah, blah. But now we have sort of to think about how we actually write functions in our code such that the compiler knows where they all exist, right? Because a compiler reads our files top down, right? So it'll compile, it'll read down through the lines of code and say, okay, cool. Like for instance, in this example here, it's going to read down and it's going to go, okay, cool, main does this, blah, blah, blah. Main calls this, this function here, get double. And it's going to go, I've never seen get double, where I don't know what this is. And then it's going to give you an error. I mean, in this case, GCC will give you a warning because it figures it out for itself, but this is bad programming practice, and this is, in my eyes, an error. So the compiler needs to know that a function, it doesn't need to necessarily know where it, like at this point in time, where it is, but it needs to know that it exists. Because it needs to know that, okay, cool, if I compile this file, am I later on, when I link my files, going to be able to resolve this function call, this object, symbol, right? And so this is the problem, is that get double here is defined after main. So there's two solutions that you have to this, right? You have function prototypes, which I have not. Okay. Yes, here we go. So what a function prototype is essentially you take the exact same format of the function and you're just putting a prototype. You're sort of like saying, hey man, to the compiler, I know you haven't seen this function yet, like the actual code implementation, but it exists. I guarantee you it exists. I promise you it exists, right? And so when the compiler runs down this, it's going to say, oh yeah, okay, cool. You're calling get double here. I don't know where it is, but I've seen it at the top. I know the shape, like the form it has. I know it takes in an integer, returns an integer, so it can do some sort of like type checking about, okay, cool, he's returning an int and he's saving it into an int. That's all good. That checks out. But it doesn't know where it is yet, and it's going to keep reading it. Oh, okay, here's get double's implementation, and so it's going to be able to then like finish the compilation and make sure that this line of code actually calls into this function, right? And so this is what a prototype is used for. It's sort of saying to the compiler, don't stress, it exists. Now, this is this can also be resolved by just manually reshuffling the order of your functions. I mean, sometimes you will need to create prototype because you can't have every function that's called in other functions before the function. You know, just sometimes there'll be like a looping problem. And so, but in this simple case, we could have just moved get double up the top. I mean, simple. Then it'll read down like, oh, okay, cool. There's a function called get double. It does this, and then it'll read down like, oh, okay, cool. It was called here. I've seen this. It exists. I know where it is, and I can compile. Like I can make all the links in my compiled object file. So that's one solution to it. Now, a solution that you'll see sort of, which is essentially function prototyping, is the use of header files. So header files, these .h's, and you might have seen in my examples, I was like, oh, okay, crap, I need to use printf, and then I include stdio.h. And like, why is he including a header file? A header file does exactly this. It makes these prototypes. And so if we can remember back to compilation, or if we think about how the compilation process happens, we have the preprocessor. And so the preprocessor, when it comes to include directives, it essentially copies and pastes the contents of the file that we include onto this line. So in this basic program, the contents of stdio.h is going to be copied and pasted onto this include line. And in stdio.h includes all the prototypes of, or like a number of prototypes for the function, like the library functions defined by stdio.c, right? And so when I compile this now, I'll actually end up with having all of the function prototypes that I have access to using stdio.c at the beginning of my file. And so when it sees printf, it'll know that they exist. It won't know where they exist because it's going to have, obviously going to have to take them from stdio.c, but the linker will resolve this. And so the linker will take all the different symbols and resolve the all the link errors and the link connections, or link references, I think they're called, right? And so you yourself can fix this, can use this to your advantage when you're doing your projects by, instead of creating prototypes up the top, when you're doing sort of library style projects, you can create header files that contain prototypes. So with anywhere else in your project and another C file that needs to use these functions, you can just include the prototypes so that your compiler doesn't complain that these functions don't exist, right? Oh, this is a bad picture. But here we'll see exactly what's inside stdio.c. You can see here it's essentially the same thing. It's just, as I was mentioning here, the declarations here, exactly. This is the form. It's just the same as the function without the squiggly brackets, and that's exactly what's happening here. It's the same function, it just has a semicolon at the end, right? So the usefulness of headers is that we can then put the includes of the functions that exist in there, and we don't have to continuously include them over and over and over again, or like write the prototypes out. We just write the include file, the include line, hey, like include my prototypes or include whatever, and it's just one easy line to write, yeah? It also lets you use system libraries, and this is sort of how C files interact with system libraries, by you include the header files that declare or define all of the functions that the C files, the appropriate C files expose, right? So the standard libraries like stdio, stdlib, string, what else is there? Like there's so many of them. They're sort of usually linked to a compiler, because inside these library files, there are very much device or hardware specific implementations. I mean, printf on a embedded system doesn't really work because you don't have you don't necessarily, I mean, for some embedded systems, you don't necessarily have a terminal. Like, where does it print to? Like printf on my laptop prints to the standard I/O streams of my Linux machine. But I don't have these on an embedded system. So the implementations, printf might exist so that your code compiles, but it might do nothing. Like, this is all very much dependent. So you sort of have to, generally they have the same functionality, but they're not always guaranteed to be the same.